Thank you for the invitation and thank you for the introduction. So this is the topic of the talk today. It is based on joint work with Ben from our school, University of Sydney, and Megan from School of Mathematics, Monash University. Landau-Lifshitz equations are classic in describing the dynamics of magnetization in solid crystals. So as usual, we go through the physics background for magnetization. An everyday magnet can be viewed as if it is made of many tiny magnets called the magnetic dipoles or magnetic moments. A very fundamental example is an electron. So electron has a negative charge and intrinsic spin property. So it's essentially like a tiny magnet generating a magnetic moment pointing downwards or upwards depending on the spin. Then most of the magnetic dipoles in a solid crystal are aligned in the same way, either by themselves or under some external influences. The net magnetic moment will be non-zero, and we say that the material is magnetic. Like many physics modules, instead of counting single electrons or single dipoles, we just divide the material into sufficiently small volume portions and calculate the density of the dipoles in that portion. So the density vector small m is the magnetization vector, and the size of the volume portion is chosen such that m varies smoothly across the material, hence this gradient notation. In ferromagnets, magnetization occurs spontaneously, and we will follow the saturation constraint to scale the length of the magnetization vectors to 1. So in a ferromagnet, what we see is that these unit magnetization vectors will point in the same direction in each magnetic domain, but they will have a non-uniform overall distribution across the entire ferromagnet to account for the net magnetic field. If we zoom in at the boundary between two magnetic domains, so two different colored patches, the region of transition of the m vectors from pointing downwards to pointing upwards, or vice versa, is called a domain wall. So the Landau-Lifshitz equation describes the distribution of these magnetization vectors and sometimes the movement of the domain walls. These features of a ferromagnet exists because they are energetically favored. We write here the common form of the free energy of a ferromagnet over the region curly R. It consists of many commonly known energies. The first one is exchange energy. It comes from the difference between possible alignments of the m vectors. So it's a function of the gradient of m. It's the lowest when all of the m vectors are pointing in the same direction. And this is the reason behind spontaneous magnetization. But different magnetic domains still exist because they reduce the magnetostatic energy, which is in the form of negative dot product of m and the field Hm. Hm is deduced from Maxwell's equation. So this energy is minimized when m is parallel to the field Hm. If we look back to the previous picture and take this bar magnet as an example of uniform magnetization, we see that the red arrow is certainly not parallel to the black field lines. So to compensate for that, different magnetic domains will form. There's also anisotropy energy, which originates from the presence of an easy axis of magnetization, depending on the crystal structure. Another possible source of energy comes from the external magnetic field, HA, if there is one. This energy is again minimized when m is parallel to HA. So applying an external field will cause the domain walls to move, in the sense that the m vectors will be forced to align with HA. So the domain that's already oriented parallel to HA will have an increase in size. From this free energy, we can calculate the cross-bounding effective field, in the sense that when m is parallel to this H effective, then the free energy is minimized. For a ferromagnet under a reasonable temperature, the exchange energy prevails over the rest, except for the external applied field, which is usually under the control of scientists in a lab experiment. Therefore, in literature, in the absence of HA, the effective field is often only modeled by the Laplacian. Landau and Lifshitz modeled the dynamics of these M vectors in their 1935 paper. We give a very brief illustration on the side to try to explain the terms in the equation. Let the blue vector denote the H effective field, and let the black vector denote the magnetization, or for the ease of interpretation, magnetic moment of a single electron. When an electron is placed in a magnetic field, it is subject to a torque or some force. This torque is modeled by the cross product of the field and the spin angular momentum of the electron. The spin angular momentum is proportional to the magnetic moment, and this explains this precession term negative m cross h. So m will rotate around the field h. But we know that when h is sufficiently strong, m will be driven towards it, so there must be some damping. Landau-Lifshitz modeled the damping by a double cross product. Alpha is a small positive damping constant. This double cross product counteracts the precession term and preserves the unit magnitude of m. Gilbert generalized the damping term by replacing the double cross product with this term, the cross product with the time derivative. It's quite well known that the Gilbert form and the Landau-Lifshitz form, they are mathematically equivalent, where the new precession constant gamma is essentially equal to 1 plus alpha squared. So the Gilbert form is more general in the way that it counts into the fact of the damping into the precession. And it's more realistic for real crystals. Nowadays, for magnetic storage devices, the dimensions tend to be very small. So they are subject to thermal fluctuations, which can affect the directions of the M vectors. The usual way to model this is to include a space-time noise psi into the effective field. An example of psi is the product of G and the white noise, W dot. So W is a Wiener process. This then gives us a stochastic PDE. The stochastic part is a Straton-Rich differential, which we shall explain the choice later. For this stochastic LLG equation, the existence and in some case uniqueness has been studied in the literature using Gaussian projections with Skorob theorem in papers by Brzeźniak, Goldys and Jegaraj. Also, there's a method of transforming the SLLG into PDE with random coefficients in a paper by Goldys and Jegaraj. We also have a time semi-discrete approximation scheme in literature associated with numerical schemes to prove the convergence by a paper written by Alauges, De Boer, and Houquet. For our result on the stochastic Landau-Lifshitz-Slonczewski equation, we will follow some of the convergence arguments in the first papers. So what is Slonczewski modification? The Slonczewski modification essentially gives us a term called the spin transfer torque. The idea is that instead of applying a magnetic field to represent the external influence, we can also apply an electric current to bring in the external influence on the M vectors. So the basic setup is illustrated in this small diagram. In general, an electric current is unpolarized, so it contains about 50% of the electrons spinning up, the other 50% of the electrons spinning downwards. Then this unpolarized current is passed through a very thick ferromagnetic layer with existing magnetization M1. Because the layer is very thick, so in the interaction between M1 and the spins of the electrons, the magnetic moments of the electrons will be forced to align in the same direction as M1. The resulting current is said to be spin polarized. Then the current will pass a non-magnetic spacer, which is of suitable thickness such that the current stays spin polarized when it reaches the free layer. So the free layer is a very thin ferromagnetic layer with magnetization M2. Similarly, M2 and the spins of electrons will interact with each other. So in layer 2, what happens is that we will have a coupled dynamics of M1 and M2. They will exert torque on each other. And Slonczewski modeled the dynamics as follows. The small v represents the density and the velocity of the input current. If we add another spacer and another small layer 2 just into the Q, then we can treat this spacer layer 2 pair as a typical section of an infinite nanowire. In that case, the spin transfer torque term can just be modeled as the negative product of B and the gradient of M. So the Landau-Lifshitz-Slonczewski equation is formulated by adding this torque, this transport term, into the original Landau-Lifshitz equation. This torque is actually very useful in practice, in applications, because the electric currents can switch the directions of the moment and cause the domain walls or the spacer to move. So an example is the racetrack memory device. Data is first stored as a pattern of magnetic domains in a nanowire. Then the spin polarized current will push the entire pattern up or down the wire, depending on the direction of the current. As domain walls pass the bottom of this U shape, they will get recorded or detected as bits 0 or 1. In literature, Melchior and Brzeźniak proved the existence of a global solution of the LLS equation in R3 by lattice approximations under small initial data and small currents V. Goldys and Jegaraj also studied the LLS equation on the entire real line to model for infinite nanowire. They actually gave the exact form of the static solutions and studied the stability under small currents V. What we study is a stochastic version of the LLS equation over the real line, similarly for an infinite nanowire, but with noise in the electric current. So here is the problem formulation. We let V denote a bounded function in T and X. The bound CV is related to the density of the current. Then on a filtered probability space, let W represent a real-valued Wiener process with space-time noise being G dW. G is a sufficiently smooth function, real-valued, and bounded with bounded first and second order derivatives. The bound, we follow the notation, write it as C with a subscript G. The magnetization process M takes values on the unit sphere. Its starting point M0 is bounded with magnitude 1, and it has a square integrable gradient, so we write M0 in H1 dot. Here we take the effective field to be the Laplacian. For simplicity, let's just define F to be the right-hand side of the deterministic LLS equation, consisting of the precession term, the damping, and the transport term. The transport term should have been negative V du, but we just choose to rewrite it into this double cross product following a trick in the paper by Melchior. This helps us to preserve the magnitude 1 property of discrete approximations later on in the proof. So the highlighted part is literally equal to negative V du, provided that U has magnitude 1. Similarly, we define the diffusion term, capital G, which comes from the noise in the current, so it's in a similar form to the transport term. Then we write down the stochastic LLS equation with Stratonovich noise, so the small circle here. The reason of choosing Stratonovich integral instead of Ito is that this choice preserves the magnitude 1 of the magnetization vector. So suppose we already know that this equation has a solution, and if we check the absolute value of m squared, then since rules of ordinary calculus holds for Stratonovich integral, we can easily calculate this to be equal to 2 times the dot product of m and the right-hand side of this equation. By a very simple cross product property, it just turns out to be 0. So with the initial point m0 on the sphere, m will be on the sphere almost surely for all time t. We can transform this into the more familiar Ito form with an additional Ito correction term denoted by G tilde. So G tilde contains high order terms like gradient squared or cross product with Laplacian, which needs to be treated a bit more carefully. Our main result is the existence and uniqueness of solution to the stochastic LLS equation. That is, we fix the terminal time t. We show that there exists a system consisting of a filtered probability space, a real-valued Wiener process, and a progressively measurable process M, such that M has magnitude 1 almost surely for all t and x, and M satisfies the stochastic LLS equation with continuous path taking values in a weighted L2 space. We also have the following regularity results for M, so for the L2 estimate of the gradient and L2 estimate for the Laplacian under the time integral. Moreover, we show there is pathwise uniqueness in the sense if M1 and M2 are both solutions to the stochastic LLS on the same probability space, then they are indistinguishable from each other. To outline the steps of the proof here, we will follow the lattice approximation scheme in Merhe's paper to first discretize the stochastic LLS. Then we show that the discretized equation has a unique solution MH, which satisfies some nice uniform estimates in a similar form to part 3 regularity results. Then to go from discrete to continuous model, we take a suitable interpolation, in this case a quadratic one. Then we use Squirrel's theorem to find a converging subsequence of processes. The final step is to show that the limit process solves the stochastic LLS equation and is pathwise unique. So the first step is to discretize the stochastic LLS equation. A fixed terminal time t and a mesh size h. We divide the real line into a uniform grid ZH and define the forward, backward discrete gradient d plus h, d minus h, also the symmetric discrete gradient dh, discrete Laplacian delta h. Then we consider the stochastic LLS equation on the uniform grid ZH, formulated with discrete symmetric gradient and discrete Laplacian. For simplicity, we just replace f, g tilde, and g with this fh, g tilde h, and gh, which represent the discretized versions of the original functions. Then for this equation, we would expect that the solution, if it exists, stays on the sphere and has a square integrable gradient. So it makes sense to consider the curly E space, which is the space of capital E valued progressively measurable processes. This capital EH is a discrete Banach space. It's the intersection of the discrete L infinity space and the discrete H1 space. Discrete H1 space, discrete H dot 1 is defined with the discrete L2 norm of the forward gradient. Note that I also have a L2 norm on the probability space. In general, this can be replaced by any LP norm for p greater than or equal to 2. The argument is essentially the same. And here comes our first lemma. We show that for every fixed mesh size h, there exists a unique solution MH of the discretized equation in the space curly E that we just defined, such that this solution MH stays on the sphere almost surely. The proof follows from standard arguments, so we just give a very brief sketch here. First, the functions fh, gh, g tilde h, they're all locally Lifshitz. So we can consider an approximate equation with the Lifshitz modifications fn, g tilde, and gn of those functions. So the Lifshitz modifications coincide with the original function in the ball of radius n in EH, and they flatten out outside the ball. We show that for every n, there exists a unique solution to this approximate equation by checking that the operator an is a contraction mapping. An of u is just m0, which is the initial condition, plus the integral form of the right-hand side of the approximate equation. The stochastic integral here is a continuous martingale taking value in h1. So with an isometry result and by calculation around the norms, we can show that this part enjoys the same Lifshitz property in EH, just like the Fm and the G tilde n parts. Since AN is a contraction mapping, it has a unique fixed point, which in this case is our unique solution Mn. Applying Ito's lemma to Mn squared, we obtain that Mn stays on the sphere. It's also worth noting that Mn is the local solution of the discretized equation up to the time tau n when it leaves the ball of radius n. And since Mn plus 1, they are indistinguishable from each other up to the time tau n, we can paste the solutions together. And all we have to do is to show that tau n goes to infinity as n increases. So we obtain the solution mh of the discretized equation as the limit of Mn. Now we derive some uniform estimates for mh. We show that the discrete gradient d plus h mh is bounded in a L2p omega, Lh2 space. We also show that this cross product m cross Laplacian is bounded in a L2 time Lh2 space. Similarly for the Laplacian itself. So these are our uniform estimates for p greater than or equal to 1. These are derived under the condition that the initial condition M0 is uniformly bounded in the space EH and that the noise is sufficiently small. So CG, if we recall from a few slides up, is the bound of the function g and its derivatives. The precise smallness condition for CG will be clear from the proof. For the first estimate, we aim to obtain this inequality here. So the left-hand side is what we have for the first estimate. The right-hand side contains the expectation of the gradient of M0, which is bounded by assumption. And the right-hand side contains the time integral of the discrete gradient of MH. So if we obtain this inequality, then immediately we can apply Grunwald's lemma to obtain the first estimate. For this inequality, we can apply Ito's lemma to d plus h m squared in the L2h norm. And after some calculations, we obtain this inequality for arbitrary positive constant epsilon. So let's look at what's on the right-hand side. We have a gradient of M0. We have integral of d plus hm, which is what we desire. But we also have terms like m cross Laplacian squared and a stochastic integral term. So we have to address the last two terms. Let's look closer to the constant C2 epsilon. If we take a sufficiently small epsilon and a sufficiently small CG, then we can assume that the constant in front of this m cross Laplacian m square is negative, so that we can move the entire term to the left-hand side. And so this is our new left-hand side. We still have the stochastic integral to deal with. And this can be treated by Burkholder-Davis-Gandy inequality. And at the end of the day, what we obtain is a similar estimate containing, again, the square of the discrete gradient and the time integral of the m cross Laplacian square. We want to absorb this estimate into the new left-hand side, which means we can assume that CG is even smaller so that the gradient part in the estimate of the stochastic integral gets absorbed into the piece power of the gradient part of the new left-hand side, and similarly for the m cross Laplacian square part. So these are the two inequalities, the two smallness conditions of CG that we require. Once we have that, on the right-hand side, we only have the gradient of M0 and the time integral of the discrete gradient. So we can apply Grunwald's lemma as aforementioned to obtain the first estimate. For the second estimate, we just change the subject to be the integral of m cross Laplacian on the left-hand side. Then we have the second estimate here immediately. For the third estimate, which is the time integral of the Laplacian in L2 norm, we first observe that the Laplacian of mh squared can be written as a sum of m cross Laplacian squared plus this dot product squared, thanks to the unit magnitude of mh. So we can estimate the L2H norm of the Laplacian by the L2H norm of m cross Laplacian and the L4 norm of the discrete gradient. So we need to pay more attention to the L4 norm because we already have estimate for the m cross Laplacian part. For the L4 norm, we can easily find that it is less than or equal to the L infinity norm squared times the L2 norm squared. Then by Gagliardo-Nirenberg's inequality, we can estimate the L infinity part. Then by a simple inequality, a times b less than or equal to half a squared plus half b squared, we obtain the final inequality here. So the L4 norm is less than or equal to a constant times the L2 norm of the discrete gradient to the power 6 plus half of the Laplacian LH2 norm. Then substituting this final inequality into what we had at the beginning, we can show that the time integral of the Laplacian in LH2 norm is bounded from above by a sum of the estimate for m cross Laplacian square and the estimate of the discrete gradient d plus hmh to the power 6. So that concludes the proof for our uniform estimates. Now we have the uniform estimates. We should think about how to go back to the continuous model. So we need a suitable interpolation. I write here the 3 common, well, maybe not the last one, but the common types of interpolations. Let xk be the point on the discretized real line. For a discrete function u, we denote by u hat its piecewise constant interpolation, u tilde a linear interpolation, and u bar a quadratic interpolation with this midpoint form for the 0th order term. Let's just have a quick look of how the arguments run for the classic Landau-Lifshitz equation without the noise. In that case, we will have nice uniform estimates from which we can derive weak convergence of the linear interpolation in a L2 time, L2 local intersecting H1 dot space. And we should also have weak convergence of the time derivative of the linear interpolation in an L2 space. Then by Aubin's lemma, this gives us strong convergence of u tilde in the L2 time, L2 local space, which in turn implies the same strong convergence for u hat, which is the piecewise constant approximation. Then this gives us the final convergence to the Landau-Lifshitz equation. In the stochastic LLS case, we don't have a time derivative. Our uniform estimates are built on L2 omega space, and we have a gradient term in the stochastic integral. The first 2 points can be addressed following the arguments in the paper by Brzeźniak. For the first point, there is another compact embedding result, replacing the L2 time space with a fractional weak time derivative space, so the W beta P Sobolev space, by a result from Fondley and Goldys in 1995. In order to bridge between weak and strong over probability space, we can employ Skorohod's theorem. As for the third point, the gradient in the stochastic integral, we would like to have strong convergence of the gradient to help with the convergence of the stochastic integral in the final step. For this purpose, we take the quadratic interpolation m bar, so one more order up from the deterministic version. If we look closer at the definition of m bar, we see that it has a continuous first derivative. In fact, this dm bar h is equal to the linear interpolation of the backward discrete gradient. And the Laplacian of m bar is conveniently equal to the discrete Laplacian. Then let's check the equation satisfied by m bar. We define functions f star, g tilde star, and g star in a similar way to the functions f, g tilde, and g, except we replace the real-valued functions v, g, g prime by their piecewise constant interpolations. Then we have here the equation of the quadratic interpolation m bar. It is very similar to the stochastic LLS equation, except now we have the remainder terms. If instead of m bar we have m hat here, then we wouldn't have these remainder terms because m hat being the piecewise constant interpolation will satisfy equation in a similar form to the discretized equation. So these remainder terms can essentially be seen as the difference between m bar and m hat. R0 comes from the difference between m bar and m hat, just the zeroth order term. So this converges to 0 strongly in this L2 omega continuous time L2 space. R2 m bar h comes from the difference between the two interpolations as well as their derivatives. So if we go back to check the derivative of m bar, we see that there is a Laplacian times x minus xk term. So although R2 still converges to 0 strongly, it converges under a time integral. R1 contains differences between the two types of interpolations all the way from 0th order to 2nd order. So it only converges to 0 weakly. It's also quite easy to verify that the uniform estimates are inherited by the quadratic interpolation. For instance, the L2 estimate for the gradient under expectation, the L2 estimate for the Laplacian under time integral, and the L4 estimate of the gradient. It's worth noting that the quadratic interpolation doesn't preserve the unit magnitude. It's, however, still bounded in L infinity, and we can show that the magnitude converges to 1 as h goes to 0. In summary, the quadratic interpolation is in this L2 time, L2 weighted intersecting H2 dot space. So the L2 weighted space comes from the fact that m bar is bounded. Let's give a more precise definition of weighted space. In this case, we choose a polynomial weight rho w equal to 1 on 1x squared to the power w for w greater than or equal to 1. This weight function is quite nice. It's smooth. It vanishes at infinity. It's integrable for w greater than or equal to 1. It's positive and it's bounded from above by 1. We define the weighted spaces L2w and H1w by using the weighted norms, so replacing dx by rho w dx. By convention, we can also write h1w as xw to the power 1 or 2, since h1 is the domain of the square root of the Laplacian. We can also write the dual space of h1w as xw to the power -1/2. We also write here some useful relations, embedding relations, due to the properties of the weight function rho w. First of all, the L2 space is continuously embedded in the weighted L2 space. L2W1 is continuously embedded in L2W2. So the greater the W, the faster the weight function rho decays. We also have a Galvan triple here of compact embeddings. So H1W1 is compactly embedded in L2W2, which is in turn compactly embedded in the dual space of H1W1. The first embedding can be easily shown using the Relish embedding theorem on balls of finite dimension, and then use the ratio between the two weight functions outside the ball. We also have this compact embedding, which is essentially one more order up from the first embedding. So the intersection of L2W1 with H2 dot is compactly embedded in the space H1W2. Okay, so we have the weighted space defined. Now we check the weak time derivatives of the quadratic interpolation m bar. To this end, we rewrite m bar as the sum of I0 to I4. I0 to I3 contains all the drift parts. There's no diffusion part in these terms. In particular, I0 contains all the M0 parts. I4, on the other hand, contains all the diffusion parts. Although these formulas look very complicated, we should remember that by construction, x minus xk is less than or equal to h. So this h cancels out with the h in the definition of the discrete gradients and the discrete Laplacian. So at the end of the day, we only have terms like m0. This will also reduce to just m0s. Also fh's, g tilde h's, and gh's. So we can do estimates relatively easily from the uniform estimates that we obtained earlier. For I1 to I3, we observe that fh and g tilde h satisfy this estimate here. So it's bounded in a L2 time L2 space under the expectation. So we expect a W12 time L2 estimate for I1, I2, and I3. But if we look at I4, there's a stochastic integral of the function capital GH. We will follow an isometry result from Landau and Jegaraj to show that it satisfies a W beta P time L2 estimate for beta between 0.5, P greater than or equal to 2. Moreover, for the I0 part, since M0 takes values on the unit sphere, so it has magnitude 1, M0 is in the weighted L2 space. So we have to replace all these L2s by L2 weighted for the estimate of the quadratic interpolation M bar. By a result from Simon, we know that W12 is continuously embedded in W beta P. So overall, considering each of these I0, I2, I3, I4 terms, we have that M bar H, the quadratic interpolation, is in the W beta P 0T L2 weighted space, almost surely. Combined with the previous result, we have that M bar H is in this intersection of the two big spaces. Note that the two weights W1 and W2 do not have to be the same to each other. In fact, for W1 less than W2 and for P equals to 4, we can employ a compact embedding result from Landau, Jegaraj, and Simon, which tells us that this intersection, which we denote by E0, is compactly embedded in another intersection, which we denote by E. If we look carefully, we have the Galvin triple here. So L2W1 intersecting H2 dot is compact embedded in H1W2, which is in turn compact continuously embedded in L2W2. Okay, so the compact embedding for the highlighted parts essentially is in a similar form to Oben-Lyon's lemma. With this compact embedding, the laws of the quadratic interpolations M bar on the space E is tight, which means we can make use of Skirot's theorem. It tells us that there exists another sequence of random variables, MH star, WH star, defined on the probability space, such that their laws are equal to the original quadratic interpolation and original Wiener process. Moreover, they have pointwise convergence in the space E and the space of continuous time real-valued functions. Note that by the definition of E, we now have directly the pointwise convergence for the gradient because of the choice of the quadratic interpolation. So it's this part here. Now we have new process MH star. We should look at the properties of this new process. Let's define another intersection of spaces, capital B. So the first part of capital B is the same as the first part of E0. The second part of capital B comes from the uniform estimates of the quadratic interpolation. So M bar is in the space B almost surely. We observe that this space B is continuously embedded into this space E. So by Kratowski's theorem, we know that Borel sets of B are Borel sets of E, which means under the same laws of MH star and MH bar, we can assume that MH star, the new process, takes values in B as well with the same laws on B. This implies that MH star inherits most of the uniform estimates of M bar H as long as the uniform estimates spaces are contained in B. So we have the first 4 estimates directly from Kratowski's theorem. The second and the third estimates tell us that the gradient of MH star converges to a weak limit x in this L2 space. Similarly, for the weak convergence of the Laplacian of MH star to a weak limit y. It's worth noting that MH star does not inherit the L infinity estimate from the quadratic interpolation M bar H. Because L infinity is not separable, we didn't use the non-Polish space version of the Skorohod theorem, and L infinity is not in the construction of the space B. Nevertheless, we still have an L infinity estimate for the product of MH star and the weight function. This will be sufficient for the convergence results that we need later on. Now, with the pointwise convergence from Skorohod theorem and from all these uniform integrability conditions, we have strong convergence of MH star to M star in this L2 weighted space and of the gradients immediately. Note that by uniqueness of weak limits, dm star is actually taking value in this L2 space. By the definition of weak derivatives, we have weak convergence of the Laplacian. And the Laplacian, by the uniqueness of weak limit, is equal to the y in previous slide. We can actually do better for the estimate of the gradient of M star. We can extend this norm L2W2 intersecting H1 dot to the entire dual space of H1W1. And then use the pointwise convergence as well as Fatou's lemma to obtain this inequality here. So we show that the gradient dm star is finite in this L2p. This should be 2p for p greater than or equal to 1 omega space, L2 state space for almost all time. If we look at this estimate here and the weak convergence of the Laplacian above, you'd noticed that we've already obtained the regularity results, provided that M star is actually the solution to the stochastic LLS. We also note that for the limit process M star, it takes values on the unit sphere almost surely, and this follows from a L2W weighted analog of the convergence argument of the magnitude of M star. So now we want to show that M star actually satisfies the stochastic LLS. To this end, we will need the convergence of the functions f star, g tilde star, and g star. The convergences of these functions in the L2 weighted spaces are quite straightforward by checking their components. So for the strong convergence of cross products related to gradients, we of course need the strong convergence of the gradient itself in L2 weighted space. But when applying Holder's inequality, we also need the L4 estimate and the LP convergence of the product of MH star and the weight function rho W. This LP convergence can be easily deduced from the strong convergence of MH star in weighted space and the boundedness of this product highlighted here. For weak convergence for high order terms like dm squared and cross products with the Laplacian, we'll use the weak convergence of the Laplacian directly in L2 without necessarily using integration by parts. Then passing the convergence to the functions, we just need to show that those coefficients, real valued functions g hat, g prime hat, and v hat, which are the piecewise constant interpolations of the original functions g, g prime, and v, converges strongly in LP. With these convergences of the functions, we are not far away from showing the final stochastic LLS equation. So this is our aim. We want to show that the limit process M star satisfies this equation. We can define the right-hand side to be the process capital M star. So it doesn't contain any diffusion terms. We can similarly define an expression capital M H star for the process MH star. This is motivated by the equation of the quadratic interpolation M bar H. So we have remainder terms here. If we can show that W star is a well-defined winner process, and if we can show that the process capital MH star converges weakly to both capital M star and the then well-defined stochastic integral highlighted here, then by the uniqueness of weak limit, we have the equality. For the first point, W star is a real-valued Brownian motion with independent increments by checking its finite dimensional distributions, which we omit the derivations here. What's more important is the two convergences. For part 1, we can make use of the previous compact embedding of L2W2 in the dual space of H1W1. So for weak convergence on this dual space, we can make use of the weak convergences that we proved earlier on the L2 weighted space. So if we check the terms in MH star, which are small MH star, F star, G tilde star, and the remainder term, so if we check the convergences of these terms individually, we can easily obtain the convergence in part 1. For part 2, we first observe that the process capital MH star is equal to this integral here with respect to the approximate process capital WH star. The equation holds here because the same equation is satisfied by the quadratic interpolation. So the result about same laws is actually really useful. Then we just need to show that this integral here converges to the stochastic integral above. We can do so by checking the convergence of the function g star to g, the convergence of the remainder term to 0, and the convergence of the WH term to the actual winner process W star in limit. So after showing this convergence, in the same space, we have uniqueness of weak limit, this equality here. So if we expand the left-hand side, it just gives us the stochastic LLS equation. So M star, the limit process, indeed solves our stochastic LLS. Now that we have existence, let's prove uniqueness. Let M1 and M2 be solutions of the stochastic LLS equation on the same probability space with the same winner process. We just want to show that the difference F is equal to 0 for almost all omega. As usual, we apply Ito's lemma to df squared. The drift part of df squared can be estimated by the product of a function psi and the L2 weighted norm of f. Psi is a positive function depending on dm1 L infinity squared and dm2 L infinity squared. If you recall from the previous slide that we had estimate for L infinity norms, we can easily show that this function psi is time integrable almost surely. For the diffusion part, we follow the idea in this paper to formulate a transformation of f squared. Then apply Ito's lemma to this transformation y, we obtain this inequality here. Note that the right-hand side, dz, does not contain any drift terms thanks to the exponential transformation with the psi. So the right-hand side, z, is a well-defined martingale. In other words, it has expectation 0. This implies the expectation of y is 0. If we go back to the definition of y, f squared is 0. In other words, f, which is equal to m1 minus m2, is equal to 0 for almost all omega. And this is the end for the proof of uniqueness. Here are some references. And thank you very much for your attention.